Welcome back. This is our first of two lectures on superposition principle. So at steady state, I am writing here our basic equations, right? So for confined and unconfined on the right-hand side, the steady state equation. So again, there's nothing on the right-hand side. There's no time differential. And here is the confined case where we only have the head to worry about, and here's the unconfined case where we have the head squared as discussed many times before. The point here of rewriting those equations is that you can see they're both linear in either h for the confined case or h squared for the unconfined case. Now when differential equations are linear, we can use the superposition principle, meaning that if we know a solution, if we know a particular solution of the equation, we can sum them up, essentially. Here's the transient basic equation for the confined case, right? So again, transient meaning we have that time differential on the right-hand side, and that's what we've been using for the Wells function and the Jacob solutions, all that. So this is also linear in H, right? So whether there is steady state or transient, all these equations are essentially linear either in H for the confined or H squared for the unconfined. Now, that means again that if H1 and H2 are solutions of these equations, then H equals H1 plus H2 is also a solution. So again, this is the principle of superposition, right? So if we know two particular solutions, then their sum is also a solution of the system. For example, if we have a steady uniform flow, right, in the x direction, let's say, we know that the solution, again, for a confined aquifer, right, so the solution is just the slope, right, is just a line, essentially, right? So H1 equals AX plus B, right, in the x direction. So it's just a line. Now, if we add a well, right, so if we have a steady, homogeneous, flow in the x direction, regional flow, if you will, we have a slope that we know, right? It's just a plane. And if we add a well, again, we know the solution, the transient solution for a well, we can use the Thies equation, essentially, right? So H2 equals H0 minus Q over 4 pi T WU, which is that well function. So again, these are very standard things that we've done so far. Now, what happens if you put a well in that regional flow that has that hydraulic gradient, little a here would be the hydraulic gradient, right, the regional gradient. Well, just sum them up. So now we have the head at some point equals the regional gradient, that AX here, plus B prime now, which is basically the head at x equals 0, minus the effect of the well. So again, if you know, those two solutions, you literally just sum them up and get the general solution for the system. So this is a very, very simple one with just a regional gradient, a regional hydraulic gradient, and one well, in the x direction. But you can see how that would work with multiple wells, because this is, again, the first lecture of that series on, using well fields and multiple wells. So again, if you know the solution for all the individual wells, essentially you know the solution for the system. So again, the effect of multiple wells is the sum of the individual wells, right? So in other words, the drawdown, right, the drawdown caused by a number of wells is the sum of the drawdowns caused by each individual well. So very simple, you can just sum them up. Okay, so this is it, for this general introduction to the superposition principle. In the next video, I will show a more involved example with multiple wells. Thank you.